Okay, welcome back. Good afternoon for this final chapter on electrochemistry, or in fact the chapter on the equilibrium of the oxidation reduction reactions. And so as any reaction, also in the oxidation reduction, the redox chemistry is subject to equilibrium situations. The equilibrium might be very much to the right, and often it is in oxidation reaction, but there are certainly also less efficient reactions, and the extent to which the redox reaction is occurring actually will depend on its redox couples. And I think this is maybe something you know from earlier courses of chemistry, that any redox reaction is always consisting of two redox couples, because in fact an oxidized form reacts with a reduced form, producing a new oxidized form and a new reduced form. And so the direction of the reaction actually depends on how oxidizing and how reducing are these redox couples. And we move always to the direction of the weakest oxidant and the weakest reductant. But how do we determine what is strong and what is weak? Okay, we're going to get into that in a moment. Then we also define an electrochemical cell, and this also has energy repercussions, thermodynamics repercussions. So we will see that there's something like electrical energy, electrical work, and we can convert in such an electrochemical cell chemical energy into electricity or electrochemical energy or electrochemical work, or the other way around. And again, it depends on the direction of the flow of the energy. In spontaneous reaction, it's the system that lets electrons flow, and then you lose energy, of course, to the environment. That's negative energy. But you also have non-spontaneous systems in which the environment is giving electrical energy, electrical work, and that's an electrolysis process which is non-spontaneous. So we first will talk about galvanic cells, in which you have a spontaneous flow of electrons. So electrons are indeed what is important in redox reactions. Electrons are normally flowing from one species to the other, and we can separate the reaction into two parts. We have an oxidation half reaction and we have a reduction half reaction. And in these we actually separate the two species from each other in their different oxidation states. And so we convert one oxidation state of a species to another oxidation state. So in the oxidation half reaction, that means we actually go up in oxidation states, and that means your species is going to lose electrons. And by losing its electrons, it actually increases the oxidation state. That means the reduced form is delivering electrons, and it goes until into an oxidized form. Then in the reduction half reaction, the opposite happens. The oxidized form of a redox couple takes up electrons, and it actually lowers its oxidation state in the process. Sometimes these reactions can be quite complicated, but we start with a very simple example in which we have the reaction of zinc metal with copper 2+, and what you get is copper metal and zinc 2+. Now if we separate it, the one half reaction is about the zinc 2+, and as you can see, the zinc is delivering zinc 2+ and 2 electrons. That's one half of the redox reaction. The other half has to do with copper, and now you can see that copper is going to take up those 2 electrons and become copper metal. In the oxidation, zinc has increased its oxidation stage from 0 to +2, and therefore that's an oxidation. And in the reduction half reaction, copper is lowering from 2+ to 0. So copper salts, copper 2+ salt is reduced with 2 electrons to copper metal. Quite simple examples. You could see that this is happening by putting a strip of zinc metal in a copper solution in water, and you can see that it's copper because of the blue color. That's typical for copper salts. They have blue or green colors depending on the counter ion. In this case it's copper sulfate, but in fact the counter ion doesn't change, doesn't make much of a difference. It's a reaction with the copper 2+. So you see this strip in the beginning of the reaction, and then after some time, when the reaction went on, it's going to look like that. As you can see, the solution is a little bit less blue. It's light blue now. That tells us that some, or maybe most, of the copper 2+ has gone. So, and what has happened with it? Well, it has been converted to the copper metal, and that's this black stuff. Small particles of copper that are being formed at the surface of the zinc. And after some time you will see that it starts falling off, and they're actually gathered at the bottom. At the same time, zinc goes into solution, but zinc is colorless, so you can't really see that from the color. Just you see that the color is getting a bit less because copper is disappearing. You also see that it stops here, so you need contact of your aqueous solution with the surface of the zinc. Otherwise, nothing is happening. So this is a kind of proof that indeed the reaction happens at the surface in the solution. If you look at it as an equilibrium, you will see that zinc and copper are solids, and zinc 2+ and copper 2+ are in the aqueous phase. So this would tell us something if we talk about the equilibrium, of course, because only the zinc 2+ and the copper 2+ are changeable concentrations. Okay, so this is a galvanic cell made from the same components, copper and zinc. But what is different from the previous one, in the previous one we had everything in one beaker, in the same compartment. And now we are actually separating the two electrodes and the two compartments. So the zinc is on this side. There's a zinc electrode, a strip of zinc which conducts electrons. And there's a copper sulfate solution in which we have a copper wire, and the two are connected. So electrons can flow through this wire, which might be any metal that conducts electricity. We can also put a voltmeter in between to measure that there is indeed some kind of potential between these two electrodes, between the zinc electrode and the copper electrode. And because of this potential, electrons will start flowing from the zinc electrode. Electrons start flowing, and zinc 2 plus will actually start going into solution. That will mean we lose electrons and we have positive zinc 2 plus. So normally that will mean we charge up this part and it becomes positive. The electrons go here and we lose copper 2 plus because it converts into copper. So that would mean we actually get negative charge on the other side. And that's of course not good, because that is energetically unfavorable. So we want to restore the charges, otherwise we have a short circuit if you talk about electricity. And this can be done by having a salt bridge. The salt bridge here, the salt is inserted into kind of paste which cannot flow out, but the ions can migrate. And the ions can then come in on this side to restore the charge, which is in this case 2 negative, so positive charge can be added like sodium ions. It's a sodium chloride salt bridge. Or on the other side, we can also migrate chloride ions to compensate for the loss of electrons that we have over here. And that way our electrons can continue flowing. So another way to do that is actually weld the two compartments together, but have a kind of plate in between, which is semi-porous, and which also leaves room for the ions to migrate. So we can still say that we have two compartments in that case, but there's no real physical separation. So indeed, each part of this galvanic cell we can call an electrode compartment. So there's a zinc electrode and there's a copper electrode in this case. And so by connecting it up and having the possibility of a flow, indeed, that's what will happen spontaneously. And this will happen until we still have electrons to give away from the zinc to the copper. That means there's still zinc present, and there's still copper 2 plus at the other end that can be reduced. As long as we have that, in principle, the reaction can go on. So, indeed, the different half reactions happen in the different compartments. So we actually separate them from each other. In the previous one, where we had one beaker with everything together, actually everything happened in the same phase. So in the other compartment, we actually have the copper 2 plus, which is being reduced. Normally we could see that by the color of the blue salts being diminished after all. So cathodes and anodes are different electrodes and can be found in different compartments. So the compartment in which you have the oxidation is called the anode, and the one where you have the reduction is called the cathode. And I know it may be difficult to remember, but maybe a small trick. Anode starts with an A, and oxidation has an A, not reduction. Cathode starts with a C, reduction has a C, oxidation doesn't have a C. That's how you could remember which is anode and which is cathode. So in this case, we have our zinc electrodes. The zinc is being oxidized to zinc 2+, so zinc is the anode in this case. And copper, then automatically the copper electrodes, there the reduction of copper 2+ to copper is happening, so that's the cathode. And so when we connect an anode with a cathode, we have the possibility of electrical flow happening. In general, for the reaction to be spontaneous and for the electrons to flow spontaneously, we will have to have a more positive potential than the anode. So, and you have in fact a potential difference between the two anodes. So, a positive potential means the reaction can go on. Now, potential is expressed by capital E. And in a situation where we have two different compartments with two different electrodes, an anode and a cathode, so the sum potential is defined as the difference in potential between the anodes and the cathode. This is actually something that can be related to thermodynamics, and I will give you more details in a moment. But as all thermodynamic parameters, we can also define them under standard conditions. And standard conditions is as usual, meaning all the concentrations that are changeable are at 1 molar. All of the gases that are present are at 1 atmosphere. The temperature normally is changeable, but the data that you find in the table for the standard reduction potentials are all at room temperature. 25 degrees Celsius, 298 degrees. It's important because you will see that it's related to free energy, so that means it's actually also temperature dependent. Okay, so the salt bridge is there to restore the charge disequilibrium that we could have as a result of the electron flow, and that way we restore the cycle. This is a little bit more elaborate drawing of this galvanic cell based on zinc and cadmium and zinc and copper. So it's also more conventional, because the convention is always to put the anodes on the left and the cathode on the right. So this is now a better way of writing it. You can see the two electrodes are in the solution of the respective salts of zinc and copper. And what you can see is that there's indeed a salt bridge. Sodium moves to the right side, chloride moves to the left side. There's also a connection, and this connection is also to the voltmeter. And potential is expressed in volts. So the reading that you see there is a difference in potential between the electrodes. And by the value that I see here, 1.1, I know already that actually the concentrations of the zinc are under standard conditions, namely 1 molar of zinc 2 plus and 1 molar of copper 2 plus. Now what is happening? If you look at the surface of the zinc, you can see that zinc is actually losing electrons, and these electrons are moving throughout the zinc, and they're moving to the right, from the left to the right, and they go to the compartment where you have the copper over the voltmeter and so on. At the same time, the zincs that have lost their electrons, they're zinc 2 plus, and they are water soluble, so they migrate into the water. So that means the surface here is slowly eating away zinc by zinc onto that electrode. So this is called in electrochemistry a sacrificial electrode, because it's being used up in the process. At the same time, so the electrons move here, and again at the surface, now copper 2 is going to the surface, not away from it, to the surface, and is getting electrons, and the copper metal is being deposited onto the surface, and small crystals of copper are forming. Now here you see how it looks like after this has been going on for some hours. You see our zinc anode, there's almost nothing left of it. It has been eaten up almost completely by the process of the zinc 2 plus leaching into the solution. At the same time, you can see the copper cathode has grown, and there's these kind of crystalline small particles of copper. Doesn't look very regular. That has been deposited on the surface of the copper. You also can see how far was the contact of these electrodes with the aqueous solution. So because until here, you see that it's eaten away, and above it still the normal size, so it was not in contact with the zinc 2 plus solution. And the same thing with the copper cathode. So also was only inserted up to a certain point into the copper 2 plus solution. So it means if you want to go on, you will have to replace this electrode after some time. Because otherwise zinc is gone, and then there are no more electrons to flow from the anode to the cathode. Okay, let's look at this from the thermodynamic point of view. We know already work as expansion work. So when a gas expands, so it's does a certain, that corresponds to a certain amount of energy, which is expansion work. But this is now electrical work, and that means we displace electrons. That corresponds to a certain charge as a result of a potential difference. And the work can actually be seen as the product of these two. Now the potential difference, that's E or delta E. And so, or E of the cell is indeed the difference between the two potentials of the two compartments. Now N and F, what does that mean? F is actually what is the charge of 1 mole of electrons. That's 96,500 coulomb. That's how much 1 mole of electrons has as a charge. Now, often a certain oxidant or reductant has more than 1 mole of electrons. Suppose if you go from an oxidation state of 4 to 2, that means 2 electrons are involved, and N is 2. Also from zinc to zinc 2 plus, that's 2. So In some cases, there's only one electron, then N is 0. What also is apparent is that this electrical work is flowing from the system into the environment. That means it's energy that is lost, and therefore there's a negative sign. The work is minus NF potential difference. Again, it's good to look at in what direction is the flow of the energy. And that's for a galvanic cell, and that's for a spontaneous process. Now, if you look at the formula that we have seen earlier for the free energy, delta G, which is delta H, the entropy, minus T delta S, the entropy, and we can split up the entropy in internal energy, difference of internal energy, and the term P delta V. And we know that delta U can be divided into heat and work, Q and W. And Q actually is T delta S. So this actually can become quite, let's say, simple, especially if we keep the volume constant. Or if we keep the pressure the same. In that case, T delta S we see on both sides, so we can cancel it. And if the pressure is constant, in fact, then also these two expansion parts are cancelled. So that means this just leaves only the electrical work part. So that means in these kind of reactions, electrochemical reactions or redox reactions, we will only consider the electrical part of the energy. And we know already that this is minus NF potential. So this now becomes one of alternative formulations again in the context of redox reactions. So delta G is minus NF cell potential. Again, with N being the amount of electrons that is exchanged between the electrons. We can also write that in the standard form, of course. That is delta G standard is minus NF, and then we also have to use the standard potential. And these standard potentials are in fact available in tables. And you can look at your table 11 to find it. Okay, so the important fact is that concentration of the reagents that we are using in our redox reaction does influence the potential in an important way, and there is an equation for that. And the equation can be derived from what we have seen earlier in the thermodynamics chapter. So delta G is the delta G in standard conditions plus a term which involves the concentrations, which is LNQ multiplied by RT. So, and LNQ is the natural logarithm of the expression that is of the same form as the equilibrium constant, but does not have the equilibrium concentrations. So, if we have equilibrium, in fact, then LNQ becomes LNK, and delta G becomes 0. So that, but at the moment when we start connecting our two electrodes, we are not at equilibrium, because the electrodes are flowing. So there's still something going on. So, this expression, we can convert into an expression that goes about potential, because there's a direct relation between delta G and potential. The factor that we have to multiply it with is minus n Faraday. So if you divide by minus n Faraday, so we get the cell potential at any concentration is the cell potential under standard conditions. And this is then, well, this factor has to be brought or subtracted from it. RT, R is the gas constants, thermodynamic gas constant, so 8.31. T is the temperature in Kelvin. NF, that's the same factor as before, so the amount of electrons. The Faraday constants, 96.500, that's 96,500. And the LNQ, again, is the negative, not negative, the natural logarithm of the expression that looks like equilibrium constant, but isn't, because we have the concentration at any moment. So this is a natural logarithm, and people prefer having decimal logarithms. So this is now converted into the expression which you find the most in handbooks. So to convert a natural logarithm to a decimal logarithm, so the logarithm that has 10 as the base number, you just have to divide by 2.303. So you fill that in. You fill in R, which is a constant. You assume that it's at room temperature, 25 degrees, so 298 for T. And then Faraday is 96,500. So all of these numbers are inside of this 0.059. So that's R, T, F, and the conversion of natural to decimal. The only thing that we cannot already fill in is N, because we, well, for every reaction it could be different. So it could be from 1 to 6 electrons, sometimes even 7. So this is the Nernst equation in the form that we will actually use it. Now Q is of the same form as equilibrium constant. That means we only take the changeable concentrations. If there are any solids or liquids, like water, that are not changeable, we will not see them in the Nernst equation. So if you apply this to our reaction that we had between zinc metal and the copper 2+, so we have two things on the left side and two things on the right side, but the zinc metal and the copper metal are solids. So the zinc 2+ and the copper 2+ are in solution. So these are changeable concentrations, and that's why they actually end up in our Q. So the zinc 2+ is the product of the reaction, and the copper 2+ is the starting material of the reaction. I already filled in 2 as N, because there are actually 2 electrons that are involved when we oxidize zinc to zinc 2+, or when we reduce copper 2+ to copper. But it's per reaction. So in this case, in the reaction there's 2 electrons involved. Now the number 1.10, I'm coming to that. This is actually the reduction potential, or the difference in potential between the reduction potentials of the anode and the cathode. Now, how do we get to this number? For that, we need the table 11. Because for each half reaction, based on different metals and their oxidized fault, we get their reduction potentials. And making the difference of these reduction potentials give you the cell potential. But more about that in a moment. Now, what can we conclude from this? So that means your cell potential is going to be around 1.10, but it actually may, depending on the concentration of zinc 2 plus or copper 2 plus, it may become bigger or smaller. Yeah. Actually, it depends on the ratio of zinc and copper. If there is as much zinc as copper, if the concentration is the same, the logarithm is the logarithm of 1, and that's actually 0. That means, in this case, your cell potential is the standard potential, 1.1 volt. In all of the other cases, it's going to depend on the ratio. So suppose you have 10 times more zinc than you have copper. So then you have a logarithm of 10. That logarithm of 10 is 1. Okay. So then that means you will have to subtract about 0.03, so 0.059 divided by 2. So now your cell potential will be 1.07. So it's going down. Suppose it's the opposite. So you have 10 times more copper 2 plus, then you have zinc in your solution. In that case, it's logarithm 1 over 10. That's minus 1. In that case, we have to add 0.03, and then your cell potential becomes 1.13. So you see how, in which direction we can go with the potential depending on the ratio of these two concentrations. In fact, during the cell reaction, normally the copper 2 plus will be going down and down and down, and your zinc will be going up and up and up. So that means this factor here in absolute value becomes larger and larger, and at a certain point this whole logarithmic factor will be equal to 1.1. At that moment your reaction is finished, because your potential is 0 and you are at equilibrium. Now about this potential. In fact, you have a potential to oxidize and you have a potential to reduce. And both are going on in the reaction. So, of course, for a certain species, the oxidation potential and the reduction potential are related to each other. Because, for instance, a reduction potential is about reaction of zinc 2 plus 2 electrons gives zinc. So there's a certain potential to do that. The oxidation potential is the opposite. So that's zinc going to zinc 2 plus and 2 electrons. So that means it's negative. So just the sign is changing if you just change the direction of this potential. So that means in the reaction that we have between copper 2 plus and zinc. So we reduce copper 2 plus, so we could discuss the reduction potential. of copper 2 plus to copper. And at the same time we oxidize the zinc. So we could add the oxidation potential of zinc 2 plus and zinc. Now, but we know that oxidation potential of zinc 2 plus zinc is the same as the reduction potential, but with a minus sign. That means to determine any cell, including the one between copper and zinc, we just need to know only the reduction potentials and make the difference in the reduction potential between these two reactions. But then we look from the viewpoint of zinc 2 plus being reduced to zinc metal, which is not what is happening, it's the inverse that is happening. That's why we have the minus sign. This again is similar to kind of Hess cycle that we have. In general, it means we look at the reduction potential at the cathode and the reduction potential at the anode, and we look what this is. Stop alarm. Do you have any experience with this? Is this time for evacuation? No? I hope it doesn't mean that I have to stop speaking. But okay. Seems to be alright. So in general, the potential of the cathodes, where the reduction is happening, and from there we have to subtract the potential of the anode. So cathode was in this case the copper compartment, and I guess we any idea what this is? You didn't have this before?
Yes, we do.
Well, if the building is on fire, let me know. So in this case, it means the potential, reduction potential of the copper 2 plus copper minus the potential of the zinc 2 plus zinc. So also mentions, well, you have potential, but only thing you can actually mention is, or measure, is potential difference. So in general, we use a standard halogen electrode, and artificially we put this to be at a potential of 0. So everything is relative to that, and some will have a positive potential as compared to the standard halogen electrodes. Others will have a negative potential. What does it mean if they have a positive potential? Is that they are stronger oxidants. And so, for instance, copper 2 plus has a potential of 0.34 volts. You can find that in table 11. So that means it's more strongly oxidizing than H plus, which is the oxidant in the case of the standard halogen electrode. So, on the other hand, zinc has a negative potential for reduction. It's a weak reductance, that's what it says. It's a strong oxidant, so in the case of copper, because it's positive. And so, and now we have to make the difference between these two. So this is what we found in the book of table, and it's not table 12 in your table book, but table 11. So you find plus 0.34 volts for copper to plus copper, and you find minus 0.76 volts for the zinc to plus to zinc. Minus minus, of course, plus. And if you add it up, you get the value that you saw there in the graph, 1.1 volts. So this is this standard hydrogen electrodes, how it looks like. There's actually, it's a little bit inconvenient because you need to bubble hydrogen at the pressure of 1 atmosphere, so at ambient pressure, over a platinum case. So there's a surface of platinum. The platinum is connected to an electrical wire. In the solution we have H+, because that's the other carbon. That's the oxidized form. H2 is the reduced form. So the H+ is at the standard concentration, that means 1 molar, or in other words, a pH of 0. So we just have, we make sure that we don't get oxygen to have reaction with the dihydrogen that is evolving. And so you need a connection, that's on the top, with another compartment. And then you can see how much potential there is between this and the other compartment. And since this is by definition 0, so the difference is automatically the potential that you have at the other side. It's in principle easy to calculate, but it's just not so easy to make this hydrogen standard electrodes, because you need some flask where you can bubble through the dihydrogen. And in principle it's a little bit of danger because of the possibility of a fire with very flammable dihydrogen. Okay, so maybe we'll take a break here and then continue after the break. If you have any questions, I will be here to answer them. Need to be conducted. And so conduction can be by copper wire, or by metal wire, or by moving of ions. You can have conduction. And if you're in water, you have to move your charge by moving your charge species. So then if you move electrons into the solution becomes negative. And the solution has to stay neutral. Can only stay neutral by micro. Okay, so this is another expression of the dependence of the potential based on the composition in the electrode compartment. Now, what we have here is we have the electrode compartment with the copper electrodes inside of a copper 2+ solution, so it's a 1/2 of the Daniell cell. And instead of connecting it to the Daniell cell of zinc, we connect it to the standard hydrogen electrode. And this is what happens when you would measure the potential of that copper compartment. And now, in general, the copper can have a certain concentration. So the reaction can be seen as the following. So copper 2+ is being reduced by hydrogen. That's the other component, the other electrode component. And you get copper metal and 2H+. Now, this is then the Nernst equation. So, the potential of such a setup is the potential of copper 2+ to copper. And the difference, of course, is with the standard hydrogen electrode, but we don't have to take the difference because it's 0. This potential, by definition, the standard hydrogen electrode is 0. And in this logarithmic term, we only take the changeable concentrations, and these do not include copper because it's a solid. Now, we could also include the H+ and the H2, which is a gas, but we are with the standard hydrogen electrode, so this is respectively 1 atmosphere and 1 molar. So that means we don't have to write it also because it all becomes 1. So the only changeable concentration now is the copper concentration. If that copper 2+ concentration is also 1 molar, then this becomes a logarithm of 1. And what we are measuring is going to be the standard potential of copper 2 plus to copper. So that's a very simple way to measure that E0 value if you didn't know it yet. We just have to connect it to the standard hydrogen electrodes, take a 1 molar solution of copper and then put in a copper electrode. If of course the concentration of copper is not 1 molar, this is going to change. So if it's 0.1 molar, for instance, then the logarithm becomes the logarithm of 1 over 0.1, so that's logarithm of 10. So in that case, we will be 30 millivolts lower, as we have seen before. So then it's not going to be 0.34, but 0.33, 0.7-ish. Anyway, in general, we can make an expression like that, reformulate the Nernst equation, and in general, for the changeable concentration, we can say A is the concentration. But for the non-changeable ones, we can just put A is 1. In other words, they don't count, because multiplying by 1 or dividing by 1 is a zero operation. If there are gases, we have to use the partial pressures. But there are not that many oxidation reactions that use gases. If you have hydrogen, for instance, that is possible. Now going on with thermodynamic treatment of redox potentials, we see a direct relation between free energy and the potential, reduction potential. So that means the same kind of transformations we can do for free energy, we can also do for the potential. And we know already that we can combine reactions, we can add up reactions, or we can subtract reactions. And then we could combine in the same way the free energy. That means we're also going to be able to, in the same way, to combine the potentials and calculate new potentials for reactions that we combine from two known potentials. So let's look here at different oxidation states of copper. So the one we already know is copper 2 plus. Taking of 2 electrons, and that is the half reaction to copper. And this is the most common way to note half reactions is an equality sign rather than an arrow to show that it's a half reaction rather than a complete reaction. But okay, this notation is not so important. The second reaction is the one where copper 1 is being reduced to copper metal. This will have a different potential. And then the third one is where copper 2 plus is being reduced, but not to copper metal, but to copper 1. Now the potentials of the first and the second reaction are known. And we can see that the third reaction is actually the difference between the two reactions. So if we subtract this here, if we subtract this, 1 electron goes away, the copper goes away, and this is minus copper 1, so it goes to the other side. So we can do the same thing for the free energy, and we can do the same thing for the potential. So here you see it for the free energy. It's just the third one is the first minus the second. and we know that delta G is minus NFE. So we can do the same. We divide the whole thing by minus NF, and we think we could also just make the difference between the two potentials. But it is not so simple as that. The problem is, if we divide by NF, our N is not every time the same. In our first reaction we have 2 electrons. In the second and the third reaction we have only 1. So that means we will have to take it into account, and in fact substitute 2 here, 1 there, 1 there, and then divide by F. And then we won't make a mistake. So in fact it is 2 times 0.34, which is for the first reaction, and 0.52 is for the second reaction. This subtracts, and then we arrive at 160 millivolts, which is the potential of the third reaction, and we just calculate its. So if you do this kind of combinations, watch the size of N, otherwise you could make a mistake. So other ways how we can get the potentials of certain reactions in which the metal cation is taken away as a precipitate or as a complex is by combining reactions and doing a similar treatment, only the calculation a little bit more complicated. I will show you in a moment. So let's look at the reduction by silver plus silver 1. Now what we already know is a reaction here. Silver plus electron gives silver metal. But what about the same reaction but with silver chlorides? So the silver is not free in solution but is a precipitate. Is this also working? And what will be the reduction potential? Now, to do that we have to involve a second equilibrium, and it can be shown that the third reaction is the sum of reaction 1 and reaction 2. So as before, we can do a free energy treatment, and that means free energy of reaction 1 and free energy of reaction 2 is the free energy of reaction 3. So it looks like that. Now the free energy of this second reaction, which is a precipitation reaction, we cannot write it with a potential because it's not a redox chemistry, but we can write it as minus R ln KSP. So we know these KSPs from table, I don't know, 6 or something like that. So we can actually fill it in. And now we divide by minus NF. And minus NF, so we have the Faraday constant and we have the amount of electrons that are involved in the first and the second reaction. And first and the third reaction, which is 1 electron. So N is 1. So the KSP we know is 2.0 10 to the minus 10. So now we have to fill this in. These are the free energies. Here we divide by NF. The minus already was dropped. So what we see here is, this is the potential of free silver, which you can find in table 11. That's 0.80 volts. It's a relatively strong oxidant. We multiply with Faraday constants, 96,500. We add up RT ln KSP. R is 8.31. It's rounded up. The T is 298. room temperature, 25 degrees Celsius. And ln KSP is the negative logarithm of the natural logarithm of 10 to the minus 10. And this we still have to divide by the Faraday constant, 96,500. Yeah, I know this should be a comma. It's 96,500. Yeah, that's in Europe we use a comma where you would use a point and the other way around. Sometimes I mess it up. So it should be a comma because it's 96,500. And if you calculate all of that, because these are all numbers that you can calculate, you end up with 230 millivolts. So that means the precipitation, and using silver chloride instead of free silver, brings it down from 800 to 230 millivolts. So it becomes a weaker oxidant. Well, what about if we take away the silver as a complex with ammonia? Now we have to do the same kind of treatments, combine reactions, and reaction 1 is the same as free silver being reduced to silver metal. The second reaction is the complexation reaction between silver and ammonia. And we know the free energy of that reaction because we also know the equilibrium constants, Kst, and that's 1.7 10 to the 7th. We have encountered that before. So that means now third reaction is actually reaction 1 minus reaction 2. So that means we have to take all of these things into account. It's something similar to this, but this will actually be minus here, and this will be 10 to the 10 to the 7th and not 10 to the minus 10. So, when you do this calculation, I'm not sure in the details, but it follows that now you have 370 millivolts. So also here we have more than halved the potential of the free silver. In principle, you could also measure the potential and then calculate Kst and or KSP from it if you have a solid or a complex. So that's another way to do that. You just measure potential and compare it to the free ions, and then this kind of calculation can be done. But then the unknown is different, and it can be converted to this unknown. So, in a redox equilibrium, there's a relation between the potential difference in the cell of the reaction and the equilibrium constant. And here we have the expression which is the Nernst equation. So, the cell potential is the standard cell potential minus a logarithmic factor. So the reaction proceeds and moves towards equilibrium. And equilibrium is the moment when there is no longer any potential. In other words, when the cell potential becomes 0. And at this point, we reach also the equilibrium concentrations. That means ln Q is actually ln K. So that means the cell potential becomes at that moment, or equalizes to 0.059 divided by n log K. this is another way of writing it. In here, if you write it to log K, that means you can directly get the decimal logarithm of the equilibrium constant from the cell potential, standard cell potential, which you multiply by the amount of electrons involved, and you divide by the factor 0.059. We have to be at room temperature for this. And so these will be K at 25 degrees Celsius, 298 Celsius. Otherwise, of course, it's not correct. So we can come to the same conclusion by deriving it from these two equations, but it amounts to the same thing. So let's take a few examples. So for instance, a zinc copper cell. What is the corresponding reaction of zinc metal with copper 2 plus, giving copper metal and zinc 2 plus? Well, first of all, N is 2, it's a 2 electron process. The cell potential at standard conditions is the difference in standard potentials of the two. That's 1.1 volt. We already calculated that. And this we have to divide by 0.059. So if you do that, we get a number of 37.3. And that's a decimal logarithm. So that means K actually is a very big number. It's 1.9 10 to the 37th. A huge equilibrium constant. That's sometimes quite normal in the reactions which involve oxidation and reduction, especially if you have a very big potential. In general, what you can say is that for any reaction you determine what is happening at the cathode, so in other words where the reduction is, what is happening at the anodes, where the oxidation is. You look at their standard reduction potentials and you make the difference between the two standard reduction potentials. This you multiply with the amount of electrons that is getting exchanged in the reaction, and then you divide that up by 0.059. And that gives you the logarithm of the equilibrium constant. And okay, cathode is reduction, anode is oxidation. It's again repeated. So the value of the equilibrium constant for a reaction that is spontaneous, we expect it to be positive. And that means the potential at the cathode should be larger than the potential at the anode. So that's for instance what we see in the case of copper and zinc. One is 0.34, the other one is minus, so it's certainly smaller. So we cannot expect the reverse reaction to be spontaneous, because then you would let electrons flow from a negative potential to a positive potential. That's not spontaneous. In that case, your K will be way smaller than 1. And that will be a reaction that will go in the direction of the starting materials. So, we will have another example that we will calculate based on equilibrium constant that we will also be able to derive from the potentials. So it's a reaction of cerium 4 plus with iron 2 plus. Now we have two half reactions in cerium and in iron. And so the half reaction of cerium is cerium 4 plus an electron that gives cerium 3 plus. The potential for that is big, 1.76. We know it's a very strong oxidant. But iron 3 plus is also an oxidant. It can take up an electron and it forms iron 2 plus. But as you can see, the potential, reduction potential, is not as high as the corresponding cerium. So that means if the iron 3 plus is the weaker oxidant, that's what will get formed. The cerium 3 plus is the weaker reductant, so this will get formed. So that's qualitative, based on the potentials, but we can now also quantitatively express what is the equilibrium constant. So the amount of electrons is 1, so N is 1. This is the potential difference. It's 0.99 volts, 1.76 minus 0.77. And this we divide by 0.059 and we arrive at 16.8. And that's of course a logarithm, so if you convert it to the ground number, that means now we arrive at a K of 6 10 to the 16th. Again, a very big number. Yes. So let's go calculate how much cerium and iron we still have in some case where we know the concentrations in advance. And now the cerium is 10 millimole and the iron is 5 millimole. So that means the iron 2 plus is limiting. It will disappear completely based on this very big K. Completely, all except for a very small amount. And let's call it X again. That means the cerium 4 plus, the same amount has to disappear, 5 millimolar, you get 5 millimolar left. And this very, very small amount X, but we can simplify that. How much cerium 3 plus is forming, how much iron 3 plus, 5 millimolar. Minus X plus. That's not going to make a difference. So we immediately fill in 5 millimolar 3 times for the two products, for the starting material, the cerium that is still left. So an X for the very small amount of iron 2 plus, which you will have. So we can simply bring all of these terms to one side, and then you will see that X is indeed very, very small. 8.3 10 to the minus 20. That means the amount of particles of iron, given the fact that the Avogadro number is of the order of 10 to the 23rd, means that in a liter you are going to have only a few thousand of iron 2 plus particles, which is a really, really small amount, undetectable amount. So that means such kind of reactions proceed until complete exhaustion of the iron 2 ions, or in any case of the reagent, which is limited. Now there's also an influence of the pH. And if you look at the table 11, you will see that there are a number of columns. In the first column you see the species. In the second column you see it is at acidic pH, the value, and at the other side is in basic pH. And the reason is that there is often a very big influence on the hydroxides, ion concentration, or the OH minus concentration on the reduction potential. Also, the species that exist in basic and acidic solutions are not necessarily the same. So here we see an example in acidic medium. So we know that it's acidic medium because we see protons in our half reaction. And if you have protons, they're always on the left side. So on the oxidized form, because we always have oxidized form plus electrons equals reduced form plus some other stuff. So in this case, the protons are there, electrons are added, 2 electrons, because we go from manganese 4 to manganese 2 oxidation states. So the 2 oxygens of the manganese end up as water. So manganese dioxide is not soluble in water, it's a solid. In case you wonder, how should I know that? Well, this information is in the table. That is a solid. So that means concentration of manganese dioxide is not present. What is present is the concentration of protons and the concentration of manganese 2+. If you put that in your Nernstian equation, so this is 1.23, that's the value that we found in table 11. And here we have the ratio of the concentrations. Now, as usual, we can split up the logarithm. And the logarithm of 1 over h plus to the 4th power can be split off. That's the negative logarithm of the 4th power of h plus, or that's 4 times the logarithm of h, of the negative logarithm of h plus, and negative logarithm of h plus is pH. So that means you have 4 times 0.59, and you divide by 2, so that's 2 times 0.059, or that's 118, multiplied by pH. What does that mean? If you're in the standard condition, so your pH is 0, 1 molar concentration of H+, this will drop. But if you, for instance, have a pH 1, so which is still acidic, but not as acidic as pH 0, you're going to drop 118 millivolts in your redox potential. So that means your manganese dioxide works not as good in pH 1 as in pH 0. Of course, it's manganese dioxide, the manganese 2+ concentration is also important. But that will depend on the situation. But just based on the pH, you can see there's quite huge effect. Okay, so here we have the quantitative influence on pH on redox equilibrium. We use K for that, and we use another very strong oxidant, namely bichromate, Cr2O7 2-. That's a strong oxidant. It has an E0 of 1.33 volts. So we're using it to oxidize iron, and dichromate and iron are in the ratio 10 millimolar to 30 millimolar. And we do that at 2 different pHs. Now the reaction, I guess we have it over here, yeah. So the reaction here, 6 irons, 14 H+, that means your reaction is hugely dependent on the H+ concentration. Even a small difference in acidity is going to make a huge difference. And you should realize that at pH 0, your concentration of the H plus is 1 mole, so extremely high. But at pH 5, your concentration is only 10 to the minus 5 of proton concentration. And so this is to the 14th power. So that's 10 to the minus 70. That's a huge effect. But let's first calculate our equilibrium constant. So we can calculate that this again very huge, 8.9 10 to the 56. How do we do that? Well, N, the amount of electrons that are involved in the reaction. It's bichromate, so bichromate goes to 2 chromine 3 plus. That's 2 times from 6 to 3. So 2 times 3 electrons, so 6 electrons in total. This is the reduction potential for bichromate. This is the one for iron, which we have seen previously. So, and we divide